Hello and welcome to Coffee and Control, the podcast where I find fascinating people from within the world of control and convince them to answer all of my questions. I'm your host, Lucy Hodgins, and my guest today is a postdoc at Chalmers University of Technology in Sweden. So I reached out to her via email a few months before the European Control Conference to ask if she was going to be there, and if so, would she mind recording an interview? Because her PhD thesis covers a load of different interesting areas, including model predictive control, which has come up in passing quite a few times on this podcast, but it really deserves covering in more detail and kind of having an episode where it's the main focus. So I'm hoping this will be more of an introductory episode into MPC. I've tried to edit in bits to make sure no one gets lost and hopefully put into context a little bit on how this guest's work fits into the wider literature. So buckle up and get ready to learn all about model predictive control, tube-based MPC, adaptive cruise control, integral quadratic constraints, linear fractional transformations, and much more with my guest this month, Dr. Ying Shuai Quan.
So my name is Ying Shuai Quan, and I work in autonomous driving. I'm mostly applying optimal and robust control.
So the first question I ask most people is, what drew you to control? Because I saw you did an undergrad degree in control science and engineering.
Yes.
Is that right? So kind of how did this come about?
It's actually in my time, and when you choose the major in our bachelor university, control engineering is the most popular one, because for a high school graduate, you don't really know what you exactly want to do in the future. But control engineering is like a broader area compared to others. So just give me 4 more years to think about it.
This right here is one of the things that I absolutely love about control, because it doesn't limit your options because it comes into literally anything, which means you can start off doing one thing and applying it in one area and then shift to something entirely different. I was at a networking event recently where one of the speakers talked about being a control engineer as being like a kid in a candy shop and just being able to go between so many different things and just explore so many different areas.
So your PhD was on robust control of autonomous vehicles. So how did you end up in this PhD in this area?
The lab I worked in South Korea, it is not only on control, but more focused on autonomous driving. And so each lab member will have different focus. So I was in charge of path planning and control, and then just naturally I came to uncertainties such as environmental uncertainties, and then become robust control.
So there are quite a few kind of interesting topics you touched on throughout your PhD. So both in terms of kind of the practical side and the control side. So I think my plan was kind of to go in chronological order through the chapters of your thesis and then maybe touch a bit on the work you've done since then. So the first few chapters of your thesis focus on adaptive cruise control, right? So a kind of basic grounding, what's the control objective in this case? What kind of the inputs, outputs and constraints involved?
Yeah, so I use the simplest model, which is a generative vehicle longitudinal dynamic model. So it's like the input is the desired acceleration, and then the system state will be ego vehicle's velocity and also acceleration.
So just a quick terminology check before we continue to make sure everyone's all on the same page. So the ego vehicle is essentially your vehicle, so the thing that you're trying to control. The longitudinal dynamics are the dynamics traveling forwards and backwards, and the lateral dynamics are related to left and right movement. Maybe this is common knowledge, but I did once ask at a conference what was meant by longitudinal and lateral dynamics, and the speaker was very confused as to how I didn't know this.
The objective is you want to follow the preceding car, but in a safe distance. And also you need to follow the physical limits of the vehicle, you must have some limits on your acceleration or braking force. And also, the most important one is the driving comfort for the passengers, because I've done a project considering motion sickness for 2 years, and we've done a lot of experiments when it comes to motion sickness. And I personally found longitudinal is the worst, especially when you have this constant like acceleration and deceleration.
So we didn't actually end up discussing this motion sickness project in much detail during this episode, but as part of the project, Ying was involved in filing 2 patents, which I had a little look through, and I wanted to summarise here because this is a really cool project. The general idea is that you collect passenger data from sensors placed on the head and torso of the passenger, and then you use this to generate a motion sickness model based on the mismatch between the motion of the passenger and their internal models. So if you're not aware, the reason why you get car sick is because the balance sensors in your ears send information to your brain to say that you're moving, but your eyes are often sending signals to say that you're still. For example, if you're kind of staring straight ahead on a straight road or reading a book, your brain is getting the same information from your eyes as if you were still. And this mismatch between the different signals being sent to your brain is what makes you feel kind of sick and dizzy. And I remember growing up that my dad used to tell us that evolutionarily, the main reason why your brain would be getting different information from different sensors was if you've been poisoned, which explains why you feel sick when this happens. Anyway, going back to the control side of things, from this model mismatch, you can then predict a motion sickness index. And the idea is that you then control your vehicle in order to minimize this index.
In terms of kind of control approaches, so your thesis had a particular focus on integral quadratic constraints, right? Could you kind of give an overview? What are IQCs? Why are they useful for robust control of autonomous vehicles in particular?
Yes, so IQC is quite nice. So if you go to the classical control theory and so do the classical method for robust control, what you want to do is for system uncertainty. So you know part of the system, and that part of the system you're quite confident about. So maybe it's a linear system. But then there's another part of the system you're not very sure about it. And so you will leave it out. So the whole system will be a connection of a very known system and an unknown part. And for the unknown part, you do know something about it. So you know the input and output of this unknown part. And if you collect the behavior of the input-output pair, you can actually replace it with another system, so which is called filter. But the thing is, the input of the filter will be the input-output of the uncertainty. And this filter will have a very clear dynamic. So then instead of analyze a known system connected to an unknown thing, now you're analyzing a known system connected to a known filter. And then based on this whole system, like augmented system, you can just apply for like Lyapunov-based analysis and put a lot of like LMI kind of condition on it. So it's quite nice.
LMI stands for linear matrix inequality, and this gives a way of formulating a large number of different problems as a convex optimization that can then be solved computationally. So one example is that they give a way of designing controllers to ensure various performance and robustness criteria are met. If you're interested, I've put some links below as to where you can find out more about them. Now, going back to Ying's thesis, chapters 3 to 4 were on using tube-based MPC. And as Ying explains, IQCs give a very neat way of designing these type of controllers.
So I was doing adaptive cruise control, and I want to do some robust control. And then at first, I want to try tube-based MPC. So the main idea of tube-based control is, so you think you're controlling the state, but that might be wrong. So you're controlling this nominal state, and you're designing your controller based on the nominal system model, but you have a real system model here, so the response you get from the real system model might be different with the thing you expected. And so the goal of the whole controller is like the aerodynamic means the arrow in between the true state and the nominal state. And you don't want this arrow state to go unbounded. You want it to stabilize this aerodynamics. So that's why instead of just using one controller, for example, it can be MPC, you add this extra feedback controller to make sure the arrow state will be always constrained in the tube. So the designing process is like you find a feedback controller K, And then you iteratively keep using this K to find this tube, which is control invariant. But then I found with adaptive cruise control system, for that model, I can't find a converged tube. So it's like just keep calculating in MATLAB. So, and then I was thinking, isn't there a better way to just find it like in one step? And then I found like this accuracy-based problem is quite, because it's very general. It's like basically any kind of uncertainty, if you can find the so-called filter to describe it, and then you can just analyze with existing control algorithms.
Ying just gave an overview of tube-based MPC, but I figured that maybe not everyone listening to this podcast would be familiar with regular MPC, so I'm going to give just a quick overview. If you're a control expert, feel free to just skip the next 20 seconds or so. So, model predictive control is a very common control algorithm, and as the name suggests, it involves using a model to predict how your system is going to respond to a given input sequence. So, given your current state, you work out what the best sequence of inputs would be to achieve your desired objective, given the system constraints. However, because in reality there will be some noise and disturbance, instead of applying this entire sequence in open loop, you just apply the first input in the sequence, see what happens, so what state you end up at the next time step, and then you recompute the optimal input sequence, and you just keep doing that. So MPC is great and can be applied to a wide variety of situations. However, there are some definite challenges associated with it, as Ying now explains.
MPC is a very nice algorithm if everything fits into the assumption. But I find one of the problems is the feasibility of MPC. So it's an optimization problem with a long horizon, and if in practical applications you have a bunch of constraints, and how do you make sure like at least this time K you might have feasible solution, and what about the next time?
So here a feasible solution means that there exists some valid sequence of inputs that ensure that the resulting states stay inside the constraint set. So if you're in a state where whatever inputs you apply, you're going to end up violating your state constraints, then that's an infeasible problem.
And so normally you will have a terminal set constraint to make sure you have feasible solution. This is the standard MPC formulation, but it is based on a lot of special conditions. So what if the constraint is not known a priori, like what if there's moving obstacles, so your constraint is always changing. So that might be one of the big problems. And also, of course, like uncertainties of model mismatch or external disturbances.
This lack of knowledge about system constraints links very closely to Ying's more recent work on safe MPC. So keep that in the back of your mind. We're going to return to that a bit later on in the episode. But aside from constraint violation, there are also some other disadvantages of classical MPC that mean that it's not necessarily ideal for adaptive cruise control.
Adaptive cruise control is one application, but we have uncertainty and disturbances. So there's a lot of algorithms you can use. But back to that time when I chose tube MPC, I was choosing in between, like say min-max or like some other algorithm. And
Ying mentioned min-max MPC here, so I just wanted to jump in quickly to say that, as you might expect, this approach involves optimizing for the worst case performance with respect to uncertainties. And whilst it's not widely used for linear systems, it has been used quite a lot for non-linear systems or linear parameter varying systems.
To be fair, like in vehicle applications, like computational time is quite important. Tube MPC is very nice because it's offline. You calculate this tube, and you just online you just put this value to tighten your constraints. So that's why I chose that one.
Could you kind of talk us through how constraint tightening is carried out for adaptive cruise control?
Yes, actually I didn't mention before, but it's quite important in the tube control. So when you design controller, mostly you have this constraint. So what you're doing is you make sure the nominal state is satisfying these constraint. But the thing is, the true state is different with the nominal state. But the thing we did before is the feedback control law. We make sure like the arrow in between true and nominal state is already bounded, and we know the bound. We calculate it based on the choice of the feedback control law, and so that we tighten the constraint a little bit, so that the nominal state will satisfy a slightly tighter constraint. So when the worst case coming, if the true state is like it's different from the nominal state to the bound, and then the true state still satisfy the original constraint. So that is the very important step of tube control.
Okay, this is maybe a bit technical, but it seems from your papers that constraint tightening relies on linear fractional transformation of the uncertainty. So kind of how does that work, and how do you decide how much you need to tighten the constraints?
Yeah, that's a good question. LFT is the method I use to leave the uncertainty out of the system. So with LFT, I will get this thing with a known system and connected with the uncertainty. And this uncertainty, like I say, using IQC, you will have a filter dynamics to replace it. But how to find this filter dynamics is also based on LFT. So LFT is a way to find the right IQC to cover the uncertainty. The whole process is using LFT. I have this connection of known system dynamics and the LQC-based filter. And then after LFT, I will have an augmented system. And then based on this augmented system, I will design a controller such as the aerodynamics is bounded.
So we've discussed the need for constraint tightening and how you can transform uncertainties using LFTs and then design your controller based on this. But you might be wondering what kinds of uncertainties you actually encounter in adaptive cruise control.
So at first, my first paper used the uncertainty parameter in powertrain system. And I talked to my supervisor, and he suggests the wind gust can be one of the other quite important uncertainty source. So the wind will affect the car by this like aerodynamic force, and aerodynamic force is some quadratic form of the relative velocity. But the relative velocity is actually the combination of vehicle velocity and wind velocity. But normally people just approximate like the relative velocity just the same as the vehicle velocity. But what if the wind is quite strong? Then you can't do it anymore.
So you've mentioned CBF, so control barrier functions. So chapter 5 of your thesis looked at tube-based control barrier functions in the context of unknown input delays, right? So first question is, what are control barrier functions and what are the advantages of using them?
Yes, control barrier function is, so you have a safety set. So what you want to do is you want to stay in the safety set forever. And how to do it is like the design definition of this safety set is some certain H value is always non-negative in this safety set. So when you're about to escape from the safety set and you touch the boundary of the safety set, and what you want to guarantee is the derivative of this H function will always be, say, positive at the boundary, and then you will be dragged back to this safety set. So it's a constraint to drag you always back to safety set.
Now, one question I had whilst researching this episode is how do control barrier functions relate to MPC? And can you combine them into a single controller? And it turns out there are quite a few different authors who've used control barrier functions within MPC as a way of ensuring safety. And in order to explain how this works, I'm going to go into a bit of a deep dive into the detail on MPC. This is going to end up being a pretty long side note. If you don't care, feel free to skip through the next few minutes. So, one concept that I realised when researching this episode that I didn't really understand is stability of MPC, so the conditions under which the system will converge to a desired equilibrium. Intuitively, it feels like MPC should just naturally be stable, at least if you have a perfect model information and no uncertainty. Like, if you're going to work out at each step what the best input is and apply this, surely your resulting controller must be stable. But it turns out it's a little bit more complicated than this. So, I mentioned earlier that MPC solves an optimization problem to find the optimal input subject to some constraints. And there were some early papers on MPC that showed that for linear time invariant systems, if you solve the optimization problem over an infinite horizon, so for all future times, you'd get a stable controller. However, obviously solving over all future times is going to be very computationally intensive. So MPC generally solve this problem over some finite horizon. So you look at the next n steps and you work out what the best input would be just over those n steps. And then you apply the first of these to the system and then repeat that at each step. But when you actually do this, you end up having to impose extra conditions to ensure that your controller does converge to your desired equilibrium. So as is generally the case in control, there are a few different ways that you can do this. So approach 1 is to use contraction constraints to ensure that your state decreases over time. Approach 2 is to add a terminal cost and constraint set, so that after n samples, you reach this desired set and your cost is constant and fixed. So if you remember, this terminal constraint set was mentioned by Ying earlier in the context of ways that you ensure feasibility of the solution. And then approach 3 is to design the cost function that you're minimizing to be monotonically decreasing over time. And one way you could do this is to use Lyapunov functions. So Lyapunov functions are used a lot in control, especially for nonlinear systems, to prove that a system is stable. So if it starts in some region, then it will remain in this region for all time. Or for asymptotic stability, if a system starts in some region, then it will converge to the equilibrium point. And a control Lyapunov function is used to check whether there exists some input that will bring the system to the equilibrium. And it turns out the one way to establish whether a cost function is monotonically decreasing and the resulting MPC design is stable is to prove that this cost function is a control Lyapunov function. So, what does this have to do with control barrier functions? Well, control barrier functions are actually very similar to control Lyapunov functions, but they end up being less restrictive. And this means that you can ensure the safety of MPC by showing that the cost function acts as a control barrier function. And there are also researchers that have combined both of these approaches to generate control Lyapunov barrier function-based MPC, which can be used to prove both stability with the Lyapunov part and safety with the barrier function part of the control scheme. So that's been a bit of a side tangent on MPC and CBF, so control barrier functions. Now we're going to return to discussion of how you can design control barrier functions using integral quadratic constraints.
So what are the advantages of using IQCs in CBF-based control design? And could you give an overview of kind of your approach to doing this?
Yes, I think it connected to the previous question you asked, what is tube-based control? So instead of using your original controller, you always add a feedback control. And this original controller, it can be any MPC or CBF-based controller. So it's basically the same idea. So with constraint tightening, you shrink the safe set a little bit. So as long as your nominal state stayed in this more conservative safety set, then your true state will be in the real safety set. And then I also read another paper is about dealing with uncertain time delay. And the way they use is to change the CBF constraint directly.
So I mentioned that your work has looked at using CBFs for systems with unknown input delays. So what got you interested in this particular problem and what kind of systems have unknown input delays?
To my understanding, it can exist in most of the real-world applications. Whenever your actuator, it can never be exactly be there on time that you expected. So I think it would be very broad applications.
I did a quick search and just a few interesting examples of systems with unknown input delays. So, firstly, for aerospace control systems, delays may arise from communications delays or delays in executing commands sent to the actuators. In connected platoons of automated vehicles, delays in measurements and things like braking and throttle execution can all be modelled as unknown input delays. And finally, in glucose regulation in diabetes, there's often an unknown delay between the level of insulin and the patient becoming abnormal, and this then being detected by the sensor and the insulin pump responding to it. So this very much highlights the importance of the work Ying is doing and also the broad range of areas that it could be applied to.
So how does constructing an IQC representation of uncertain input delays differ from the types of uncertainties you were dealing with in the previous chapters of your PhD?
Yes, so the previous one is about parameter uncertainty. So that one I used the LFT. So it's a long existing classical control method. And for time delay, it's like you know the bound of this time delay, but you don't know the exact value of it. And you collect all the frequency domain responses. And then you found this description from frequency domain to time domain, and you found this filter dynamics for this time delay.
So your work makes use of high-order control barrier functions. So how is this different from first-order CBF, and why was it necessary to use higher-order CBFs?
Actually, the advantage of CBF is dealing nonlinear dynamics. So with nonlinear dynamics, if you using CBF, you can after all have a linear constraint. With it's a constraint on only control input. So by applying this CBF-based constraint on control input, you can actually make sure the system state stay in the safety set. So it is very nice. You're not directly putting the constraint on the system state, but you're just putting constraint on control input to make sure it's safe. But the thing is, using the method of CBF, not every system can get a constraint on control input in the first step. Because to get the CBF constraint, you need to calculate Lie derivative based on this system dynamics. And sometimes you just found, so say, if this constraint shape as A times U less than B. And then sometimes you calculate, and at last you found this A is a 0 value. So that is purely because of the relative degree of the original system dynamics, and along with this safety set. And then you found you need to do the derivative again. So that is like a second order system. And then if the A value it's still 0, and then you then need to do it again. So the goal of high order control barrier function is to make sure you have a control input constraint.
So one of your papers, so your control systems letters paper, it stated that it had a limitation that only works for linear systems.
Yes.
Do you have any ideas of how this could be extended in future to non-linear systems, and how much harder that would be?
Yeah, I was thinking about it. As long as you can lift your nonlinear part. Say you have a nominal linear system, and then you lift the nonlinearity out of it. And this nonlinearity, is for example, slope restricted, and then you can find an accuracy to describe it, and then finally we can have a LMI to calculate the tube. So because we need a final augmented linear system to build up this LMI. And I was in one of the presentation today, and they were saying so you need to linearize the nonlinear system, and the linearization error can be described by IQC too. So then with their method, I could think is possibility of extending it.
So I'd now kind of like to move on slightly to discussing your work on lane keeping systems. So I understand a lot of your work in this area is focused on designing systems that can deal with variation in longitudinal speed. So what difficulties does that variable speeds generate in the control problem?
Yeah, that is simply because when we're using lateral vehicle dynamical model, mostly you assume the vehicle speed is constant. So sometimes you just put 30 km per hour or 80 km per hour in the system model, and you don't change it in your design. But the problem is when you do a very emergency lane change, sometimes you do change your velocity, and then it will affect the control performance of it. And in the case of lane keeping, it's normal human drivers when they come to the curve section, and then you will tend to reduce your speed a little bit. So then in that situation, the system model won't fit for your actual system anymore.
So, in terms of like the approaches you've used for this problem, it seems you've done quite a bit of work on using neural networks. So why are neural networks useful for lane keeping systems?
Yeah, it's at first like it's a trend to use learning in control, and so it's MPC is very computationally costly, and so at first we were thinking about just use one neural network to approximate the whole control law. And that's how it came. And then we figured like recurrent neural network is quite nice because it has all the information of the past, so it will make the prediction more reasonable. So that's why I use that.
So how do you ensure that this kind of machine learning based approach generates a robust or safe control strategy?
Yeah, that actually goes back to the IQC again. It's like the reason we say neural network is like a black box is it's because it's highly nonlinear. It's a little bit hard to describe and analyze it, and because the weighting in between layers are linear, you can consider it as an actual linear system model, but at each neuron you have a nonlinear activation function, so that makes the whole analysis very complicated. And say again, it's the same thing. You have a linear system model, which is all the weightings of the neural network, and you have the activation functions. And that thing is the thing you don't really want it, and so you lift it out. And the good thing about all the nonlinear activation function is that they are all slope restricted in between 0 and 1, and then you will find a filter to replace this nonlinearity. So after using IQC, you will have an augmented system, purely linear, to describe the input-output behavior of the neural network. And then you can do all the classical control method, like say you want to know the robust stability, or you want to know the robust performances.
I just wanted to quickly mention here that a lot of the concepts cropping up in this episode, so things like LMIs, IQCs, and neural network stability analysis in particular, link very closely with topics covered in an early episode of this podcast with Matt Turner. So I've linked that below in case you fancy checking it out. And I've also put a link to the transcript if you want to just like skim through and find the parts that you're interested in.
So, as well as robustness analysis, you also carried out reachable set analysis, is that right? So what did this involve and why was it necessary or useful in that case?
Yes, reachable set analysis in my paper is actually the same with robust performance. It's like when the input have disturbances, or like I have a slightly different unexpected input to the neural network, and I want to know how the output will change. The output should be bounded to a certain range. So that is why I called it a reachable set. When I have uncertain input, I want to know the output of the neural network, like is it bounded in a set. The reason why it's important is because I apply this neural network as a controller in my closed loop system. So when I have a slightly different input, I want to know like my output, how much it's changed, so that because my car is completely controlled by this neural network, and I want to know how the state of my car will change. So, for example, like there's some obstacle in front of me, I want to know will I have any chance to run into it.
So, one of your early papers in this area examined using multi-model recurrent neural network control for lane change systems with speed variation. So could you explain how this controller works and how it's able to deal with longitudinal speed variation?
So at first, my supervisor said, like, oh, you should try to use this neural network to train this MPC controller. But the thing is, of lane changing, you have so many different situations, like you have different velocities, and what if you change velocity in the middle, and I can't generate infinite scenarios to cover all the possibilities. Like, so if you're driving in 80 km per hour and now you saw a car in front of you, you do an emergency lane change and you reduce to maybe 30 or 40. And in the procedure of reducing the velocity, there's so many possibilities. And so then we figure out, like, instead of just generate infinite scenarios, we focus on generate data with one constant velocity. And then this is offline training, so we will have a bunch of RNN, like neural network, with different velocities. And then online, we have the current velocity, and then we found the weighting for the current velocity, so that we combine the result of all the neural network controller and then get one control input.
I've definitely mentioned on this podcast before that I find multiple model controllers just really interesting. So I wanted to add a little bit of context in terms of how Ying's approach compares to the approach that I've used previously. So Ying's controller finds the output of a bunch of different neural network controllers and then blends them together. But an alternative approach is to switch between different controllers designed for different models. So at each time step, you just use the model that's closest to the current system. So I have linked a thesis in the description that gives a really good summary and lots of theory behind multiple model switched adaptive control, which is definitely worth a read if you're interested. And whilst the multiple model switched framework can be really nice in terms of provable convergence criteria, you can get issues related to switching in terms of kind of how frequently you switch and making sure you don't get discontinuities. So using a weighted combination like Ying did gets around these issues and ensures that the control input remains smooth even when the velocity changes very rapidly. And obviously that's quite important when you're in a driving situation.
So your later work used a linear time varying form. So linear time varying form for MPC to then train a single recurrent neural network controller. So kind of how did this differ from the control design perspective and in terms of performance to the multi-model approach?
Yeah, I will say like they works better in different applications. So for multi-model, I think it works quite well for lane change because you don't really know how you will change the speed, but for sure you will like reduce the speed. But I think LTV MPC is better for lane keeping and especially for the curved road because like how it works is in our lab we do have a real car experiments. So we drive along like a curvy road all over Korea. So we have a lot of data. It's quite nice. And so we were thinking about how to fully use it. So offline we have a lot of data. And one problem of like varying parameter in MPC is like MPC is have a prediction horizon. But if your speed keep varying, you don't know like in future how it will vary. But for us, it's like we have this data, and it's like very general lane keeping problem. So the data is close to human driver and follow certain like constant pattern. And so you have this data, you can just use it in offline because offline you know how future will change, but online you can't actually use it because you don't know the future. And that's why we use the neural network to approximate it so that it can be used online.
Could you use neural networks for adaptive cruise control? Why didn't you? Why might not it be as effective as kind of tube-based MPC?
Actually, one of the reasons is we don't have much like adaptive cruise control data. It's mostly when we collect data, it's us like just driving on the highways, and it's not very dense traffic.
Just a little bit of signposting. So I know I promised this was going to be an MPC episode. The next 5 minutes or so are not going to be on MPC. I had a few questions about a different approach Ying used for lane keeping systems during her PhD that I thought was pretty interesting. But if you are here for the MPC, we will come back to it right afterwards when we discuss the work that Ying is doing currently.
So the final chapter of your thesis used linear parameter varying gain scheduling control for lane keeping systems. So could you give an overview of how this worked and how it differed from the neural network approach?
So for the lateral vehicle dynamics, you have certain varying parameters. So we have 3 parameters are varying. It's some coefficient of the friction model and it's also the velocity. But 3 of them works in different roles in this model. and altogether you will end up with 5 varying parameters.
So the physical parameters that are varying here are the longitudinal velocity and the coefficient of friction on both the front and rear tyres. However, because the relationship between these parameters was non-linear, Ying instead defined a kind of 5-parameter vector that related to these 3 physical parameters in a way that meant that the overall system depended on this parameter vector in an affine way, which obviously made the control problem a lot easier to work with.
And then if you have like varying parameters more than 4, the vertex will increase crazily. So it comes to the general idea of gain scheduling control. It's like say your velocity varies from 30 to 80, and then you will have 2 controllers. One is designed at 30, one is designed at 80, and if you draw a line between 30 and 80, you can find where you are in the current velocity. So if like you're 40 now, and you will like closer to 30 and a little bit further to 80, and this is where gain scheduling works. You give like this coefficient to weight the controllers of these 2 vertex. When it comes to 3D model, you will have, for example, you have 3 vertex here, and it is convex Hall. It has to be, and then you find your current parameter, and it's inside of somewhere, and you find this coefficient and weighting. But so if you can imagine, like if you have a lot of vertex, and then it goes to another dimension, and then it's quite hard to find where you are, and it will become, so to find where you are will be computationally very costly. So that's why we decided to map it into a lower dimension and then map it back. 3 dimension is quite easily to find, and then you have each vertex, and then you do the gain scheduling control. And for each vertex, they are like in the lower dimension. And but when you design this controller for this vertex, you map it back to the original direction. So you still design it with this, for example, 5 varying parameters. And so that is why we do it. At first, we used PCA to like map it and remap it, and then we figured out like this thing might need some robustness guarantees. So that's why we used the autoencoder, because that is purely fully connected neural network, and it's easier to analyze its robustness.
PCA stands for Principal Component Analysis, and this is a very standard technique in machine learning in which you reduce the dimension of a set of data by transforming it into a different coordinate system.
I guess a somewhat related question is like, how do you ensure that this control strategy is robust?
Autoencoder is very similar with the thing I did before. It's like if you leave the nonlinear activation function out, and you can find the output bound when you have like different unexpected input to the neural network. So what we were thinking is like, now say we have this parameter reduction neural network work online, and before when we were training we didn't cover all the situations. So what if the situation like shifted a little bit and the input of the neural network is not exactly the same as we used before, and then we have this reduced, like say 3-dimensional parameter. What if it doesn't fall into any part of the convex Hall? What if it's out of the convex Hall? Then basically the whole algorithm will just like falling apart. And that's why we figure out the bound of the output. Like when we have input disturbances, how the output will change, and then we increase the convex Hall a little bit, so that when we have bounded input disturbances, and then the reduced parameter will still lie inside of the convex Hall.
So last question in this area. So one of your papers used LPV-based H2 controllers. So why was this type of controller well suited to this application? And kind of, could you apply other types of controllers?
Yes. Yes, I don't think it's restricted to H2. The reason is H2 is like for each vertex, when we design this controller, we focus on the average performance. So that's why it's H2. But if you like want to have some like peak to peak performance or like H infinite, it will all work. Just decided by how you design this.
So now coming back to something you talked about earlier, which is safe MPC and your work on that. So recently you've released a few papers on safe MPC for autonomous driving. So what's the difference between safe and robust MPC?
It is a very good question, and we share a lot of similar characteristics. So the safe MPC came up that the idea is when we design MPC for autonomous driving, we like have these a bunch of constraints, and mostly we know this constraint before. It's more like physical limitations or desired driving comfort kind of things. But the problem is like when, say, we are trying to avoid a pedestrian, and this pedestrian is like a jaywalker, and then they will do something unexpected, and then the constraint will keep changing, sometimes unexpectedly. And so that's why we want to have a MPC who always provide feasible solution, even when the constraint is changing. And so that is the idea of safe MPC. So what we do is we have a consistency condition for this unknown constraint, and we have an actual safe set. So what we do is like we want to make sure the last step of the prediction horizon, our car is always fully stopped. So we say like the safety constraint is satisfied. Mm-hmm. And so this is safe MPC, the general idea. And the similarity between robust MPC is the consistency condition I mentioned. It's actually very similar with robust MPC. It's just having a very conservative prediction of the possible position of the obstacles, so that I will always avoid more.
Your approach to safe MPC involves learning an online constraint softening. So how does this work?
So one important part of safe MPC is this consistency condition. And then, like I said, it's similar with robust MPC. It's conservative. It's to make sure that the condition holds. You basically always have the worst case assumption. But what if like even the worst case assumption won't cover the current situation? Like say, like I said, like a jaywalking person, and then you will never predict their behavior. And so that's when we decide like we calculate how much the consistency is violated. So like how much off they are behaving, and then according to that value, we decide how much we relax other constraints. For example, like we will sacrifice a little bit comfort, or like we will break a little bit more. So the previously set up constraint will change a little bit to cope with the current situation. And by that one will involve an extra optimization. So that's why I learned like a map from the unexpected behavior to how much I relax my constraint. So that's how it comes to the learning phase.
So I believe you've written a paper applying this to adaptive cruise control and lane changing systems. So how did this compare to the approaches you used in your PhD?
Yes, this method focused more on the uncertainty of the environment. It's like I still assume like my ego vehicle system is good enough to describe all my behavior, and so the robust part is about the other people. And but my PhD thesis doesn't involve a lot of interactions with other vehicles, so it's all about me. Mm-hmm. It's like how my system might be wrong, or like how would I have some disturbances on my actuary.
Whilst we're on the topic of different types of MPC, I wanted to add a little bit of extra context on the wider field of model predictive control. So robust MPC and stochastic MPC both consider systems in the presence of disturbances, but robust MPC assumes that this disturbance lies in some compact set, whereas in stochastic MPC, the disturbance is governed by some probability distribution. So the set of possible disturbances won't necessarily be compact. I was reading through a very good review paper on these that I'm going to link in the description. And it also gave a very good overview of tube-based MPC and how it can be applied to stochastic systems and also certain kinds of nonlinear systems. Also, this episode is not meant to be focusing on stochastic MPC, but I wanted to add in a little aside on an interesting rabbit hole I went down whilst making this episode. So, there was a different review paper published in 2016 that I found that was just focused on stochastic MPC. And right at the end, there was a section on applying stochastic MPC to nonlinear systems. And one of the approaches mentioned was something called generalized polynomial chaos. And just from the name of that, it just like, I was like, I have to look into that more. So essentially, this involves using a series of polynomial basis functions to approximate a random model output. And you can then use this to do a number of useful things, including using it to propagate stochastic uncertainties through a system model in a way that makes stochastic MPC for nonlinear systems computationally tractable. So I'm going to link in the description the Control Systems Magazine article that gives a very detailed overview of the maths of polynomial chaos expansion, plus a few interesting uses of it in engineering and control and like different papers you might want to read if you're interested in this area.
Your ECC paper is on safe MPC,
yes.
right? So could you give an overview of that and how it fits into the overarching work you've done on safe MPC?
Yes, it's exactly like the last thing I described is so we have an unexpected behavior of this, for example, pedestrian, and they suddenly changed, and this change wasn't covered in my previous worst case based prediction, but somehow I do know where the pedestrian is, so I know like how much he misbehaved, and then I did an extra optimization and to figure out how much I change my comfort constraint. So in this application I change the bound of the acceleration, I remember, so that I will sacrifice a little bit. And then the next step was like after this ECC paper we did something about learning this method because I considered extra optimization.
My kind of final question before we go on to the last section was, what are the other papers or areas of interest you're currently working on or that you're particularly excited about?
Yeah, I really like this, the interaction of the environment. So it's a beginning because in my PhD I didn't consider much about interaction, and so now the current work is more like I react when the surrounding changes. But which is another very interesting thing, but will the obstacle also react when I change my decision? So it will be like a mutual interaction thing. I haven't seen very thorough research about this, but it's very interesting to work on.
Okay, so I have a few kind of quick questions at the end. So the first one is, what's the best piece of advice you've ever received?
I think it's just like to have a local goal, not very global. So just focus on the local minimum. Say after some deadline, and then after that have a good vacation.
Are there any approaches to control of autonomous vehicles you haven't worked on yet but would like to?
Yes, it's by far still like all the thing I did is robust. Control is considering the worst case. But I really like the idea of like risk-aware based control. So it's like stochastic control. You have chance constraint. You don't always consider the worst. That one is quite interesting.
Are there any other applications that you'd like to work on in future other than autonomous driving?
It will be like a human interaction robot. Be quite. Like I said, I like the idea of like interaction to see like how my decision will affect the other and how they will affect me, and so interaction aware is very nice.
What's your favourite part of your job?
Actually, it's one thing about IQC, because in the beginning I found it so hard to understand, but it was like one moment I suddenly understand it. It's actually quite easy, and it's very nice and delicate algorithm. And I quite like that moment. It's come out of nowhere, but it's quite nice.
Who's your role model within the field of control?
It is a professor from ETH. It's called Melanie Zeilinger. And I was in a summer school about learning MPC. And I was very admire multiple characteristics of her. She's really good at explaining complicated things in a quite simple language, and she's very calm. And so I never felt like actually teaching can be kind of like art kind of thing. And also her research is very consistent. You can see her research is connected. It's not very scattered around.
Since this is an MPC episode, I wanted to mention a very nice review paper that Melanie Zeilinger wrote with a few other authors back in 2020. So this was titled Learning-Based Model Predictive Control Towards Safe Learning in Control, and it gave a great overview of how MPC can be combined with machine learning. So essentially, there are 3 ways this can be done. So firstly, you can use learning to improve the dynamic model of your system. So I guess this is the most obvious use of learning within model predictive control. Secondly, you can use learning to improve the closed-loop behavior by modifying the cost or constraints or terminal set. And finally, you can augment learning-based control methods, for example, reinforcement learning, using approaches similar to MPC to ensure safety. So, for example, you use learning-based approaches to find the optimal input at each step, and then you use MPC kind of like a filter to ensure that the constraints are met and the solution is feasible. And if the solution isn't feasible, then you modify the input to make sure that it is, but keep it as close as possible to the optimal input. Also, whilst doing some background research around this, I stumbled upon a seminar series that took place back in COVID times called Control Meets Learning, which unsurprisingly is on the intersection between control and machine learning. So Melanie Zeilinger did a talk on safe learning-based control. I'm going to link that below. There are also a ton of other big names in control, various interesting people. You can go watch the seminars that they gave. So people like Steve Brunton, Jean-Jacques Slotin, Jeff Sharma, Florian Dorfler, just to name a few. And then final question, what's been your favourite paper or project to have worked on?
I would say my favorite project I've ever worked on was I worked on this motion sickness reduction project. It was a 2-year project with Hyundai. That was really fun because it's not a well-researched area and we have to do everything from ground and say from system identification and all the way to the control. And the really fun part about it is we need to build up the device to rate motion sickness, and then we have to gather a lot of volunteers to do this work, and it is really fun. It's a little bit not very control theory, but somehow connected, and it's been very interesting. Yeah.
Great, thank you so much for the interview.
Thank you so much.
So there have been a ton of topics covered in this episode. I'm just going to summarise a few of the key technical takeaways. So model predictive control works by using a model of the system to work out at each time step the best input sequence subject to a set of constraints, and then applying the first input in this sequence. Robust MPC involves ensuring that constraints will be met in the presence of disturbance. And one approach to this is tube-based MPC, which involves using a feedback controller to make sure that the true state remains within some fixed distance from the nominal state, and then applying MPC to control this nominal state. Integral quadratic constraints give a useful way to design these controllers by removing the uncertain part of the system and replacing it with a filter with known dynamics, and linear fractional transformations give a way to derive this filter. Safe MPC is used in cases where you don't know your constraints in advance, for example, when controlling an autonomous vehicle and a pedestrian suddenly steps out in front of you. And the idea behind Ying's approach is that you relax certain constraints to try to minimize or avoid violating others. And finally, either as an alternative or addition to MPC, control barrier functions can be used to ensure safety, effectively by dragging you back into the safe set as you start to get close to the edge of it. So, there have been a lot of topics covered in this episode. If there are any in particular that you'd like to learn more about, I've left a ton of links in the description. So all of Ying's papers that we've discussed, plus some very good review and tutorial papers that I found during my research. I also started putting together transcripts of episodes. I haven't gone through all of the past episodes yet, but you can find the one from this interview in the description if you would find that useful. I really hope you've enjoyed this episode. Please feel free to rate and review the podcast, and you can also connect with me on LinkedIn if you want to let me know what you thought. Next month's episode should be released on the 1st of September and will be with Alberto Paduan, who I also interviewed at ECC. It was such a great experience. I cannot wait to share this episode. It will probably end up being a two-parter because I ended up talking to Alberto for almost 2 hours. It was great. I had a great time. So yes, look forward to that. But until then, I hope you have a fantastic month.